Okay, a little diversion again. Going to look at the LTE wireless technologies for connecting my boat monitor back to Google. So I was having trouble with using LoRaWAN and Sigfox to get coverage. LTE, I should get it. So let's have a look at this. I'm using a Pycom gPy board and then connecting through LTE. And initially I'm going to use LTE-M connectivity. I may look at LTE, so NB-IOT as well, which is another even more lightweight LTE technology. I may not need to use it, so I may not go down that track, but let's have a look at least getting LTE-M connected up. So let's have a look at the code to work with the LTE modem. So I'm using the gPy board from Pycom, which has a built-in LTE modem, and through that modem I can use LTE-M or NB-IOT, depending on which firmware I load onto the modem. So at the moment I'm using LTE-M. So let's have a look at my main code. So I put all this into a project called IoTBase. So I put that out on GitHub, so I'll put the link down in the bottom so anyone who wants to see the code can get hold of it. Also, for the LTE connection, I'm using Holograms SIM card. It's kind of a third party for normal carriers like Verizon, AT&T and people, but it allows the device to talk to any local network, and then all the billing and management of devices is through Hologram. So let's have a look at the code. So I bring in a whole bunch of libraries. I kind of followed the pattern I did for the other test projects for LoRaWAN and Sigfox, where I put the interesting LTE stuff down into a sub-library. So there's a library called lteHelper, where I've put the actual LTE connectivity and sending the packets. I used the library that I developed in the ourLora video number 3, where I used the PyTrack expansion board to get GPS coordinates. So I'm still doing that for this test, so I can send GPS coordinates periodically from different locations to check for coverage. So the actual code, I turn off the heartbeat blue LED on the Pycom board. I import a couple of libraries. One of them is the accelerometer library, just because I want to turn that off. I don't want to use power for accelerometer, so I'm not using it. I set up the deep sleep parameters here. Again, I think back in ourLora video 3, I talked more about the deep sleep processing. I get the GPS coordinates. I'm using that PyTrack helper library that I created again in the video number 3. And with that, I'm creating a body data string, which is just a JSON string, which has the device ID and payload fields that can contain the latitude and longitude that was collected from the GPS. So the bit that's LTE specific is to call this LTE helper send data, and I send the data that's in this body data string. After that, it just goes into a sleep. At the moment, I'm sleeping for 10 minutes. When I do this for real out on the boat, I'll probably have it wake up every 1 or 2 hours just to conserve battery. But I set up the deep sleep parameter for 600 seconds or 10 minutes, and then go to sleep. And then it wakes up, comes back around and does it again. So let's have a look at LTE helper. So in this routine, I'll skip the library import. The only thing that's different really is to import LTE from the network library. I've got the same old blink routine. So when I send data, so remember from the main, I got the GPS coordinates. I've put it into a string. That string's coming through in the body data there when I call send data. So what it does is just gives me some debugging information, sets up an LTE object based on the LTE library out of networking, and it's the LTE object. Note that sometimes if you're using with a specific vendor, you have to init to a specific vendor name and as a parameter. For Hologram, you don't need to do that. You can just do an init. I do a reset on the modem just to make sure it's all cleared out. I configure the LTE. So this is where I use that hologram identifier to tell the base station that I'll be connecting to through LTE that this is going to be a hologram specific connection. I set up the default band, and then I call LTE attach. It'll sit there and attach. Sometimes it takes up to 10-20 seconds to attach, but it'll just go through a loop, show a full stop while it's attaching. Once it's attached, then I'll do an LTE connect. So as it says there, the connect, once it's attached to the LTE network, then it needs to connect to the IP backend to be able to get an IP address and be able to do IP things like send data. So it'll go through a connect piece of code, and then here is the less LTE specific code, is really just doing normal internet stuff. So I get the address of my backend, which is ourLora.com. I set up a socket, say that it's going to be a internet socket. I'm using SSL, so I wrap that socket in SSL so I can do a secure connection. I do the connect. This is probably a duplicate, but connect to ourLora.com on port 443 because it's secure. And then I'll set up my headers that are going to go back to my backend service. So it's going to be a post. It's going to ourLora/mailbox, which is my backend Firebase function. It's an HTTP 1x1. I'll set up a list of headers here. So for my particular application, I need to set up the authorization. I need to set up the user agent so it can identify where the data is coming from on the back end. And I say the content type is JSON. So I create the headers here separated by a character return line feed. And then I do a send on the socket of my HTTP message, which is Hypertext Transfer Protocol. So it's got all the headers plus the body data in that message. I don't wait for a reply because for IoT, I'm not really checking on the device, and I can't do anything on the device depending on whether it replies that it's successful or not. So I just close the socket at that point. Then I do an LTE deint, that turns off the LTE radio. Do a blink just to let myself know that it's finished, and then I'll be returning to main, and that seems to successfully work. So let's have a look at this code running. Okay, this is sped up, but I run it on my Pycom board. It's getting the GPS coordinates. Once it's got those, then it's going to drop into the LTE routine. So it's attaching to the LTE backend, it's connecting, then it sets up the SSL connection, sends the data, then it closes out the LTE environment. So I took the whole thing up to my boat and tested up there. So you see it's blinking away, getting GPS, it sends the data, and I could check that I actually got the coverage I wanted from the boat as well. So I looked at my back end to make sure the packets were coming through from my boat, so I can see them here and Firestore that the packets have been received. I also went to Hologram to see what it was reporting on the session. Hologram's got pretty good user interface here, so I'll go into the Holograms information on that particular device. So this information here was the data I was sending yesterday about 12 PM from the boat. And we can see here from the boat, I was sending them about these ones here, so around 12 o'clock. So it's been, in this case, up at the boat is getting picked up by T-Mobile, but you can see down here other carriers pick up the content if they're closer. The thing that was interesting was the size of the packets being sent. It was like 8K, 8 or 9K for each of those IoT interactions. And because you have to pay money, each megabyte's about, I think it's about 60 cents for every megabyte. I really didn't want to spend that much. I'd expect to use a megabyte in a year, not a megabyte in a few days at this rate is what I'd use. So I'm going to have a quick look to see if there's a way of making this content smaller. But basically, okay, when I did a trace of sending just one of those packets through SSL using curl, I see that the total size is around 8,000 bytes, which is a lot more than I really want to be sending. You see a lot of that traffic is just the SSL setup, which has a lot of overhead. So I'm going to have a look to see if there's a way of communicating with the back end where I don't have to send so much data each time, otherwise I'll be burning through my hologram data allocation fairly quickly. So I've updated the code to use Hologram's middleware service, hopefully to reduce the amount of data that needs to be sent each time, basically because it won't be using SSL. So a lot of the negotiation that goes on with SSL is going to be reduced. So main now looks like this. The biggest change in here, so I need to check that the GPS actually returns a coordinate. I interfaced to my LTE helper now by setting up a Python list that contains key value pairs. So the only key value pairs I have are latitude and GPS 0, longitude and GPS 1, and a pretend value called value, which at just a moment just has a value of 1. And then I call LTE helper send data, pass the data list I've created here, and also pass this thing here, which is the device key from Hologram. Over in Hologram, this is my device definition, and what I needed to do was under webhooks. If I want to use webhooks, I needed to have a device key, so this generates one. If you don't have one, you can regenerate them if you want to have a new device key, but that's the device key now associated with this device, and that's the one that I was passing here to the LTE helper. And let's have a look at LTE helper. So the changes I've made here is send data now accepts this data list and the device key. The endpoint that my device is going to talk to is the cloud socket for Hologram IO. So there's much more up on Hologram about these things. The port's going to be 9999, and I set up a topic called sensor data. I don't actually need to use this, but I set it up anyway. Then we just go through what I showed before, goes through, sets up the LTE connection, gets attached, gets connected. Now instead of setting up a secure socket, I just set up a TCP socket. So first I get the body data as a string. So we see here I use build data up here, which breaks the data list apart and stringifies it into the correct format to pass it up to Holobyte, and that actually took me a couple of days to work out the correct format that Holobyte could actually pass the resulting data, but I have it now. So this is the body data as a string. I set up the socket. I do the connect to the address up that I defined up here and to the port. I create a data object that combines the device key. So we saw that get passed through. That's used by Hologram to work out where to send the data when it comes into its system. The body data that we created here and the topic we saw earlier. and then I do an LTE socket send, so it just sends the data again. A little bit of playing around here I had to do that. I had to worked out that I had to send it just as ASCII data. Use the send with the ASCII data. After it's done that, I don't wait for the response from Hologram. Again, the device can't really do anything with a bad response. It just sends it and hopes it makes it. So I close the socket. I do a deint on the LTE stack, so powers it down basically. Then I do a red blink, return back to the main, and so we'd come out of it here, and then I just go into a deep sleep for however many seconds I've set here. So this really does power down the gPy board and the PyTrack board. So let's have a look over in Hologram. So we can see the results of running this. If I go to status, this is today's effort with the new code. You see it comes in a variety of sizes, either just over 1 kilobyte or 1.75 kilobyte. I haven't worked out reason why I get a variety of sizes. Must be some sort of timing issue. They both get processed in the same way. So over in routes is where I set up the route to receive the data and tell it what to do with it. So I've set up this webhook router where it sends the results of the data coming in to ourLora.com mailbox, just like with the other communication methods, and then I pull the data out of the packet that's coming in from my device. So I'm getting the device ID, and I'm assigning it to a JSON field called device ID. I'm getting the latitude and the longitude, assigning them to these JSON properties here, and I'm also getting the value that I sent. So this is just an example of really 3 sensor values that I'm sending back to my back end, and we can look at all activity to see it processing what it sees in the data and where it's sending it. So this ourLora01 is where it's sending it on to ourLora Firebase cloud function endpoint. And we can go have a look over there. Okay, so there's an example of one coming in, so we can see the body, because in Hologram I'm sending the data in that format. That's what it sees the body data come in as. It recognizes the device because I set it up in ourLora. Does all the normal things of getting the device type, the sensors related to it, and then pulls the sensor, the matching sensor value, and writes it out to my cloud Firestore storage. Look at that by timestamp descending of the data coming in. So these ones here with value of 1, the ones where it's coming in. So it's got the location from the GPS. So this is basically showing that it all works. But the one concerning thing really is just that even though I've reduced the size of the transmission from 8 kilobytes down to 1 kilobyte, 1 kilobyte's still a lot. It still means I'm going to go through about a meg of data in, I think it's around 44 days I calculated. So I was looking around to see if there's other ways of sending it, maybe through UDP rather than TCP, to further reduce the actual network overhead of sending that. Haven't any luck with that yet. I'm waiting for a response from Holobyte. Otherwise I might have to put a middleware UDP server in place and then have that send the messages on to my Firebase function. Network trace of that 1K or 1.6K, depending on which way I'm holding my tongue, data. And you can see here this is 129 byte packet is really the one that contains the the data that's been sent. But wrapped around that, we have all the TCP sync-X, sending the data, getting a response, and then closing down the connection. And that adds up to about 1K in this case of data being sent, whereas really I've probably got really just this length data that I really want to be sending, 63 bytes. So I'd like to get closer to that than even the 1K at the moment, so it uses even less data across the LTE network. But that may have to wait. Anyway, I do have a reliable way of sending data from where my boat will be located through LTE and getting it back to my Firebase backend. So next videos I'll go back into Angular and look at the things I'm going to be doing to get the user interface to process the IoT data coming in, and by that time I may come back around here and see if there's a way of reducing the data overhead of LTE.